Howdy. Yes, recently I yet found another pebble, and yeah, this looked already rather interesting on the outside. The yellow color reminded me or seemed to be sulfur, and it is. It has a rather strong sulfur smell, and if you hold it in your hands will get yellow. There's this yellow dust, so the actual pebble is very soft. And I cut it open, and that's the inside of the pebble. We can observe several things. We have this black line which goes basically all around, and we have square features that are rather interesting. We have different kinds of colors, layering going on, shockwave patterns, which are, I think, these. There might be physical shock patterns, there might be also shock patterns that were created at the moment of this pebble being created. Let me show you some. No, maybe I don't. I don't have a picture of that yet. I have another pebble that has very nice shock patterns in it, but I don't think I have a picture. Yeah, I actually figured to take a picture right now, so that's the shockwave pattern I mentioned. This line, and you can see how there is a very strong discontinuity. There's something really different going on the other side of that line. And there is another one here. Maybe one here or even two. And there's one up here. That is not that strongly. But I think, or I find this part very, very interesting. Because it is in the same stone. And this is continuing throughout the stone. And that's the stone how it looked when I found it. Yeah, it's rather big, and I had to take it in my pocket and ride down a hill because I found it almost on top of a hill. But it was so interesting, I just had to take it with me, and yeah, I'm glad the pants didn't break because that weighs more than a kilo easily, and it barely fitted into my pocket. So anyway, I wanted to talk also about the dark oxygen thing, because they are talking about pebbles too. Dark oxygen discovered coming from mineral deposits on deep sea floor. Baffling new results show that rock-like mineral deposits. Rock-like mineral deposits. Yeah, that's already very baffling that they are calling that rock-like mineral deposits. I don't know. Anyway, in the deep sea can produce oxygen. Yeah, check it out, it's a pebble. It's just a pebble. Gerard Baron, CEO of the metals company, holds a polymetallic nodule. The company helped found new research that found that such nodules can produce oxygen without sunlight. Let me show you this brimstone again. Now no, it's not visible here in this picture, but there's metal inside this too. Metal flakes or grains or however they are called. So we have sulfur stone. I think these are metal flakes. I have to make some better pictures of this in order for you to see that we have an acidic stone that bears metal inside. So we can assume it could work as a battery too. But we are at the beginning of this video, and I think this could get a very long video because there's a bunch of things I would like to talk about. Anyway, let's go on. The flat pitch-black seabed of the Pacific Ocean's Clarion Clippertone Zone CCZ is littered with what looks like hunks of charcoal. These unassuming mineral deposits called polymetallic nodules host a unique deep-sea ecosystem, much of which scientists have yet to catalogue. And the deposits are also a key target for companies that are looking to mine deep sea because they contain metals such as manganese and cobalt that are used to make batteries. Yes. Now, researchers have discovered that these valuable nodules do something remarkable. They produce oxygen and do so without sunlight. This is a totally new and unexpected finding, says Lisa Levin, an emeritus professor of biological oceanography at the Scripps Institution of Oceanography, who was not involved in the research. The oxygen gas on planet Earth is typically understood to come from living organisms that convert sunlight, carbon dioxide, and water into oxygen and sugar. Now I want to repeat this sentence again because it is about something I have to talk and show you also in this video. But in order to just emphasize this, the oxygen gas on planet Earth is typically understood to come from living organisms that convert sunlight, listen closely, carbon dioxide and water into oxygen and sugar. Okay, remember that. Probably, hopefully, already knew that. But I just wanted to emphasize, you will figure out why. The idea that some of the gas may come from these inanimate minerals and be produced in total darkness really strongly goes against what we traditionally think of as where oxygen is made and how it's made. Goes against what we traditionally think. In other words, they don't think at all, they just repeat the same mantras over and over and over again. This is what tradition is. So traditionally think or traditional thinking is basically an oxymoron because you are thinking in circles, you won't get anywhere ever. But anyway, says Jeffrey Marlowe, a microbiologist at Boston University and co-author of the study, which was published on Monday in Nature Geoscience. Yeah, probably he knows better because he is working on a university. Maybe he doesn't. Anyway, the story of discovery goes back to 2013 when deep-sea ecologist Andrew Sweetman was facing a frustrating problem. He was part of a research team that had been trying to measure how much oxygen organisms on the CCZ seafloor consumed. The researchers sent landers down more than 13,000 feet to create enclosed chambers on the seabed that would track how oxygen levels in the water fell over time. But oxygen levels did not fall. Instead, they rose significantly. Thinking the sensors were broken, Sweetman sent the instruments back to the manufacturer to be recalibrated. This happened 4 or 5 times. Yes, traditional thinking. Over the course of 5 years, says Sweetman, who studies seafloor ecology and biochemistry at the Scottish Association for Marine Science. You know, chemistry. It's all about the exchange of charge of the elements. Nature searching in equilibrium. And he couldn't figure out that. I don't know. For marine science, I literally told my students, throw the sensors in the bin, they just don't work. Yeah, traditional thinking once again. Then, in 2021, he was able to go back to the CC set on an environmental survey expedition sponsored by a deep-sea mining firm called Metals Company. Again, his team used deep-sea landers to make enclosed chambers on the seafloor. The chambers then closed encased sediment, nodules, living organisms, and seawater, and monitored oxygen levels. Sweetman and his team used a different technique to measure oxygen this time, but they observed the same strange results. Oxygen levels increased dramatically. Suddenly, I realized that I'd been ignoring this hugely significant process and I just kicked myself, Sweetman says. My mindset completely changed to focus on what is causing this. My first thought was microbiology, and that's because I'm a microbiologist, Marlowe says. It wasn't a far-fetched idea. Scientists had recently uncovered some ways that microbes such as bacteria and archaea could generate dark oxygen in the absence of sunlight. In lab tests, the reproduced conditions on the seafloor in the new study that the researchers poisoned the seawater with mercury chloride to kill off microbes. Yet the oxygen levels still increased. Yes, I have been told that the sulfur that is found here, especially here in eastern Finland, I don't know, I should go in other places to check as well, but the sulfur, and like also the pebble I showed in the beginning, the sulfur pebble, the brimstone, that these were microbes doing that stuff on the sea floor or on the beds of the lakes. Yes, this is what I've been told, but I don't think so. But anyway, that's just a basic. Nah, it's not the same. Anyway, if this dark oxygen didn't come from a biological process, then it must have come from a geological one, the researchers reasoned. They tested and ruled out a few possible hypotheses, such as that radioactivity in the nodules was separating oxygen out of the seawater, or that some other environmental factor was separating oxygen gas out of the manganese oxide in the nodules. Then, one day in 2022, Sweetman was watching a video about deep-sea mining when he heard the new nodules referred to as battery in a rock, a phrase favored by Gérard Baron, the metals company's CEO. That led Sweetman to wonder, the metals that are in these nodules, could they somehow be acting as natural geobatteries? If so, they could potentially split seawater into hydrogen and oxygen through a process called seawater electrolysis. You can try this at home by dropping a small battery into salted water and watching the hydrogen and oxygen gas bubble up. Batteries in a rock was just a metaphor as far as the scientists knew. The fact that the nodules contain metals used to make batteries do not mean that they are electrically charged themselves. To create a charge, positive and negative ions would have to be separated to some degree within a nodule, creating a difference in electric potential. To see whether this was occurring, Sweetman flew to Illinois to test the nodule's electrical charge with Franz Geiger, a physical chemist at Northwestern University. Amazingly, there was almost a volt on the surface of these nodules, Sweetman says. For comparison, an AA battery carries about 1.5 volts. The researchers' leading theory is that this charge is splitting seawater to create oxygen, though they have yet tested whether disabling the nodule's electric charge halts oxygen production. The scientists plan to test this in future studies. Geiger theorizes that the polymetallic nodules become charged as they grow, with different metals depositing irregularly over time. Nodules from around a small object, such as a shark's tooth, if you cut one open, they look like cross sections of tree rings, or like layers of an onion, Geiger says. These metal layers grow only millimeters every million years, and the types of metals being deposited change over time, potentially creating a gradient in charge between each layer that results in electrical potential. That doesn't explain why there are differences in charge on the surface of the nodules, but Geiger theorizes that the nodules are porous enough to leave some of their inner layers exposed. Rocks are not known to carry charge like this, Geiger says. This is one of the most fascinating things I and my lab have ever worked on, he adds. It still isn't clear whether or to what extent these nodules create oxygen naturally on the seabed. In most experiments, oxygen concentrations in the chambers plateaued after 2 days. That might indicate that the lander changed something about the environment. For example, by kicking up sediment, which then instigated the oxygen production. It's also possible that oxygen production eventually stopped because of a bottle effect within the enclosed chamber, Marlow says. The products build up, the reactants go away, and then the reaction sort of stops. But in an open system, it could be a more consistent process, he explains. Yeah, what did you expect? Bo Barker Jurgensen, a marine biogeochemist. No, biogeochemist. Chemist? Biogeochemist. At the Max Planck Institute for Marine Microbiology in Bremen, Germany, says the findings are very odd and raise many questions. Jurgensen was not involved in the research, but was one of the paper's peer reviewers for Nature Science, Geoscience. Yeah, I don't know my peer reviewers. I just get number 2 said. I don't know the names, it's number 2. Anyway, it doesn't matter, they didn't publish it anyway. He is skeptical that these nodules produce oxygen when they are left undisturbed on the seabed. Still, he adds, it seems to be some electrolytic reaction on the manganese nodule surface that does indeed produce oxygen, and that in itself is a very interesting observation that has not been observed before to my knowledge. The researchers still have no idea what role this nodule-produced oxygen may play in the seabed ecosystems of the CCZ. Environmental surveys have shown that the nodules and surrounding sediments are a habitat for deep-sea life. Yeah, there's oxygen. What a surprise. Everything from single-celled microbes to megafauna animals that can be seen with the naked eye, such as fish, sea stars, and worms. Approximately half of the megafauna catalogued during the 2013 environmental survey were found only on the nodules. Half of the megafauna. Like most of the deep sea ocean, the seafloor of the CCCZ is a poorly understood ecosystem, Levin says. We haven't even discovered most of the species in the deep sea, let alone studied them. Deep sea mining projects proposed across the CCZ would extract nodules from swaths of the seafloor. The International Seabed Authority, yeah, SpongeBob, which governs the seafloor in international waters, is currently discussing rules and regulations for mining the nodules and other deep sea targets. 27 nations, including 26 member states of the ISA, have called for a moratorium, precautionary pause, or ban on deep sea mining. I don't think this research is a nail in the coffin for deep sea mining. That has never been the intention, Sweetman says. It's just another thing that we now need to take into account when it comes to deciding, do we go and mine the deep sea ocean or don't we? To me, that decision needs to be based on sound scientific advice and input. Oh man, I could talk days about this, but first of all, like all the pebbles I have ever shown to you weren't found on the sea floor. Okay? I have never been to any sea floor. So all the pebbles I have ever shown to anyone are found maybe at the shore of a lake, but not from deep sea floors. In other words, I don't really understand the reason why anyone tries to go there and get those pebbles from the seafloor when you can find them everywhere. Because I don't believe that every one of these pebbles down there is exactly what they are searching for. There's just maybe a small percentage of the pebbles they will mining there, which are then those they can actually use. So let me show you still something about batteries, because in my plate tectonic issues, the influence of electricity in the rock forming process and blah blah blah, part 3 paper, which is basically about peat, I talk about nature or peatlands, wetlands being batteries. Let me just scroll down. I will put a link below. You can read the whole paper on your own pace. Let me just. Maybe here it starts. Peat's active role in the environment and in the end of the last ice age. Peatlands are often wetlands. Water is very abundant on Earth, and even more than previously thought. It has specific electrical properties. Pure water is a very good insulator, but very rare to be found as such in nature because it is also a universal solvent due to its hydrogen bond variability. A wetland environment contains a large amount of impurities which can dissolve in water. In other words, the water is charged. We also have to remember that water pouring out of the ground has its own charge. which can immediately change as it comes to the surface and gets in contact with air, or basically more oxygen. Or light could be the reason too. For example, calcareous tufa depositing systems, which are found in many places in the world. Very calcium rich water comes out of the ground and it experiences an immediate change. It releases CO2 in the air and calcium gets deposited. I think raised bogs, or also called ombotrophic bogs, may have somewhat similar processes which makes them grow. The emitted gas or element might also be different. Peat has the ability to store or capture an enormous amount of water. It is a very porous material, which means the actual surface of it is rather great. When talking about surface interactions of water, we have to take into account the effect it has on the water itself. Water close to surfaces exhibits a charge differential with the water itself, or within the water itself. It is much more organized than bulk water. It is the so-called exclusion zone where we find easy water. Since water in nature is always charged to some degree, we need to assume that these exclusion zones might be smaller and weaker as expected, or much bigger, stronger, and more influential than previously thought. PhD Gerard Pollack did experiments about the water's exclusion zones reacting to metal plates. The results were unexpected but also very interesting. It turned out that water establishes connections between different metals and it also transfers charge. Water also charges metals. In one of the experiments where zinc and platinum were used, zinc is highly reactive whereas platinum is not. Zinc had immediately a strong, easy layer, but the platinum, as expected, did not. Zinc made the water also more alkaline. After connecting the two electrically with a wire, the platinum also showed easy water layer. In the paper about peat from the Journal of Physics, where heavy metals were studied, geochemical distribution of heavy metals in peat soil profile and estimation of water table patterns in peatland at Chias Peninsula, Sabah, are several diagrams shown about the metal content, and it becomes clear that iron is by far the most abundant element. Zinc plays an important role too, but at least one diagram is strangely manipulated. I am suspicious enough to think that this is not a mistake. The following picture diagram is from the mentioned paper. It's not that well visible here, but you can zoom in. Figures from the paper mentioned above note how the depth of the samples differs by 1 meter from 6 to 5. Also note how the iron concentration spikes upward from 5 to 6 meters. Why are there no measurements from the depth of 5 to 6 meters available from zinc? We can only guess. The author thinks it spikes upwards too. Furthermore, we have to know that the concentration scale is not the same either. The one on the right is 6 times smaller than the one on the right, so the spike in iron content would be much better visible if they would be similarly scaled. I just wanted to point out that if you watch some scientific papers, uh, be careful. You know? If you don't know what I mean, here we start at 200 and here we start at 50. We are going 0, 200, 400, 600 on this page or this picture. On this side, you just go from 50, 100, 150. Okay? In the author's opinion, my opinion, water plays a much bigger role in the peat world than previously thought. This conclusion is a straightforward logical assumption based on a more holistic view of the environment, which includes electromagnetism. In peatlands, in its liquid state, it is only present in its unclean form, so it works as a conductor. We have a great abundance of metals with their own charges and electromagnetic properties, and also quartz mixed together as very thin pieces and soaked in a conductive medium, water. Remember, we are in the middle of this paper, so if you want to get the whole picture, you have to read the whole paper. Anyway, just the fact alone that peat is highly hydrophilic implies that peatlands are charged waters because soaked water is basically only surface water or easy water. This, combined with all the metals included, already makes up a great mix for natural electricity circuits and charge potentials. Some peatlands are in regions with clay occurrences. Other peat regions are in limestone karst regions. Both are alkaline environments and both are strongly associated with water. Let's talk first about clay. I think that clay is an intrusive material which originates from the interior of Earth and should be seen as a volcanic element from mud volcanoes. It doesn't need heat to get liquefied, it needs water or abrasion. In other words, a mud flow made of clay isn't necessarily hot, but the water in it will eventually evaporate and the clay will get harder over time. Often the groundwater level in clay lands is rather high since it has been once a very dirty water flow by itself. Over time, thousands of years, such as sun cycles and by planetary or asteroidal encounters coupled with energy surges in Earth's circuitry itself, some of the clay got vitrified by electrical discharge events and turned into rock, which is commonly known as schist. The abundance and importance of water correlates well between peat and clay. Without it, they couldn't perform their nature and therefore their role in nature. This could explain the abundance of peatlands in clayish environments. Peat is heavier than water but lighter than peat. And where you find clay, you also have water. Of course, some aquifers might dry up because of earthquakes destroying the connection to the waters below or even excessive use by humans, so the layer of clay dries up very deep into the ground. If it dries up, it can form an almost impenetrable barrier for water, as well for water from above as for water from below. The waters from below will break through the barrier when the pressure is high enough. If the supply from the waters above is sufficient enough, it will soften the ground gradually until it's all mud again. Again, no heat needed, only water. Earthquakes will have a great influence on the aspect of liquefaction too. Clay can get very liquid very quickly, as some incidents of quick clay landslides in Norway have shown. When assuming that volcanic activity at the time of the events, in this case the focus is on water-based volcanic eruptions, such as the aforementioned mud volcanoes but also cryptodomes, was at much higher levels anyway. Then we also have to assume that the abundance of surface water and wet ground was also much greater, also without rain. Karst regions are mostly limestone and are known for the abundance of caves, gorges, but also the great amount of wells and good groundwater circulation in an alkaline environment. The formation of karst region remains a mystery in common theory of geology. Despite attempts to bring up a new explanation, the role of electricity in rock forming processes is not taken into account. Let me bring forth my own brief and therefore incomplete explanation about the genesis of karst. Limestone consists to a great degree of calcium, which has only one electron more than potassium. I think with an increased electromagnetic potential, different pressure and heat in the environment, potassium gets charged, i.e., it gains an electron, and is thereby transformed into calcium. The chemical does not undergo oxidation or a reduction process, it undergoes elemental transmutation, which also includes a change in its geometry. It is alkaline, which is a very important similarity with the kinds of minerals we find in peat. In a study about the mineral content of peat were listed several minerals which were identified. Interesting is that quartz is listed but silica is not, despite similarity of the difference being in the amorphous and or crystalline structure of the mineral, much like it makes a difference between microline and orthoclase. Something must have altered some of the materials with heat. Induced electrical currents can do that easily. In the paper, Effect of pH on the stability of quartz in a multiphase system of kaolinite, hydrous aluminium hydroxide and quartz, is shown how the pH affects chemical reactions. Again, all chemical reactions are electric events and therefore pH has to be seen as the charge and its polarity of the environment. In an acidic environment, it is positively charged, whilst in an alkaline environment, it is negatively charged. At the end, it all comes down to the amount of positively charged hydrogen ions relative to the amount of negatively charged hydrogen ions. But, basically, hydrogen is charged negatively. The hydrogen ion has a net negative charge. Hydrogen is the most abundant chemical substance in the universe. Therefore, we have to assume it is so also on Earth. It shouldn't come as a surprise that the mentioned minerals are all alkaline and mainly made from the same stuff in different configurations. pH An pH interaction with silica is an important factor. Its variability is a nice example of the dynamic nature of charge exchange valence because they can have huge influence on the environment. For example, this statement comes from a study about engineered nanosilica particles for oil recovery from the King Abdullah University of Saudi Arabia. Quote, the silica nanoparticles have a high negative charge in alkaline conditions and become slightly positive charged as pH lower than 4. Another very interesting valence process which includes silica is so-called concrete cancer or ASR, alkali silica reaction. Concrete cancer is a process where the alkaline ingredients of cement concrete start to react with the amorphous silica content of sufficient moisture if sufficient moisture is available. The result is an expansion in volume. Through the force and magnitude of the expansion, it produces cracks and weakens the construction. We have the concrete construction, which is the solid and stable part of the interaction. We have the fluctuating part, the moisture. Moisture is provided by the atmospheric conditions, so it fluctuates a lot. Compared to the state of the concrete, the main driver, it fluctuates a lot compared to the state of the concrete. The main driver behind this process is the fluctuating element containing hydrogen in different states of charge, hence ion exchange. I think the process of ASR also happens in nature, maybe invisible inside Earth. It can make mountains bulge or create land uplift. Silica collects water, which also can be released to the environment. Maybe this could happen rather quickly too. The aspect of hygroscopy is yet another important part of the energy circuitry involving water. It might be something similar to easy water, but the author isn't sure about this. Hygroscopy takes place when water molecules get suspended between the molecules of materials. It charges the material and changes therefore also their properties, such as volume, temperature, viscosity, and other properties. Zeolites are also something to take into account. They are water trapping solids made of silica, aluminium, oxygen, and alkaline earth compounds such as magnesium, potassium, sodium, plus the water molecules trapped in them. They can be produced for industrial use in order to process oil into gasoline, for example. Not only can they be reused due to their self cleaning properties, but they are also very heat resistant. We must assume that something similar exists in nature too and possibly plays an important role in natural environments. It might be one of the reasons why peat can hold so much water. The peat cloud, yeah, you have to read the paper in order. That's the peat cloud is uh, the last. Usually, peat is the top layer of the soil, and the reason for this is, I think, peat is vitrified or instantly vitrified biological matter, and it got vitrified and pulverized instantly, vitrified by electrical currents and pulverized by shock waves and very strong winds. So it got lifted aloft. It was in the atmosphere for some time. And because it's so fine grained and it's dust, basically, it was the last layer that settled down. And I think it usually settled in places that had high pressure. So, where we find peatlands, the ground might be positively charged due to the metals in the ground. That's why there has been probably a high pressure system, especially bigger peatlands. They might exhibit a high pressure system, which creates the electromagnetic vortex, and in the other, that brings stuff down. A low pressure system, if you watch at a thundercloud, the energy goes up. So we need a high pressure system in order for stuff to come down. Anyway, the peat cloud settled in places with water and opposite polarity. As described, calcareous rock and clays are alkaline, but peat is acidic. So they have a natural magnetic attraction towards each other. Another reason for why peat accumulated in certain areas more than in others might be the geological imprints in Earth's crust. Yeah, now, meaning that areas with a positive charge create naturally counterclockwise vortices, which in terms of weather means a high pressure weather system, i.e., not much of wind. The material ionized by the shock wave traveled through the atmosphere as an ionized cloud and pulled in iron from the environment. The environment might have been enriched with iron, such as Mars encounters with Earth. Maybe the deposition process was something similar to an industrial process called plasma enhanced chemical vapor deposition. Peat contains quite much iron, which is usually present in an oxidized form. The importance of iron has also been recognized in several studies about peat and is also seen such as iron or for the life form of the seas. What I find very interesting is the fact that peat contains Fa3, iron in its third oxidation state. It is the only form of iron which is useful for organisms, for algae, to humans. We should recognize this as something very important. It might be as important for Earth as it is for us. Earth is a huge organism too. A further source of iron, besides the initial aggregation through electromagnetism and ionization, could be groundwater sources with great iron content. It might be transformed from its original state when coming out from the ground into Fa3, a somewhat similar process as we see in growing tufa ditches. There are many examples of how limestone and iron go well together. Here are two, both from Switzerland, the Iron Well and Place of Power Grimmiwasser in the canton of Bern, near St. Stephan, of the Oolithic iron spherules or occurrence in the Jura Park in Canton Aargau. Not only the accumulation of the ore in layers of limestone, but also its creation happened quite likely through electrical discharge events and included a lot of water. So, the spherical iron deposits look like someone was welding with an arc welding machine underwater and it was sputtered. It should not come as a surprise that in the Jura Park are also peatlands present. Not big ones, but there are. The magnetic properties of iron change from ferromagnetic to paramagnetic at the Curie point, which is 770 degrees, which is about the same temperature which is used in glass production. Not only was electromagnetism involved in the creation and accretion of peat, it also plays an active role in the electromagnetic environment today. Peatlands are storages for water and they also can storage energy, such as heat and cold. Usually the release of the stored energy happens through water vapor and CO2, which is once again essential for plant growth. CO2 is a greenhouse gas which gets pumped into greenhouses for a better yield. As speaking of plant food, light might play a very important role in some of the chemical reactions happening in peatlands. Light has many different wavelengths and intensities, so we have to think also about the influence of sunlight on peatlands. It is well known that Siberia has very vast peatlands and it is very cold in the winter and very hot in the summer. The author thinks that the Siberian traps, the largest basalt accumulation on Earth, with their high metal content, have an influence on the regional weather. Positive ground charges seem to attract high pressure systems and are therefore responsible for the clear skies. Sunlight might change. No. Sunlight might charge up peatlands. Elemental transmutation takes place at a more rapid pace, which might also explain the bigger CO2 emissions. Some radiation coming from the sun or even further away penetrates quite deep into the surface, and as earlier shown, some materials like zinc are more abundant in deeper layers of peat that could experience charging. An example of how light with a specific wavelength can trigger a chemical reaction is an experiment made by Chris Kramer, which has the name hydrogen chloride cannon. The first thing which came to the author's mind when he saw this hydrogen chloride cannon were the mysterious craters of Siberia. The region where those craters form is within the auroral oval. The author, me, think it is possible that strong atmospheric disturbances can create such strong magnetic fields that also daylight, not only auroral light emissions, could be funneled or pinched into certain wavelengths in such a way that they could trigger an ignition. Solar activity and fluctuations in Earth's weakening magnetic field only enhance such possible mechanisms. A sudden peak in telluric current intensity and the brief establishment of a strong connection between the ground and the heavens is probably the best path to find out what is behind the mystery of these craters. A big problem in investigating the relationship between solar activity and the crater formation is that those structures are in very remote areas. No one really knows when the explosion happened. If we would have once an eyewitness report or some satellite observation about the exact time of such an explosion, we possibly could make a significant step toward in order to prove or disprove the theory of the author. It also needs more investigations about the atmospheric processes the author tried to express. Visual pattern recognition is an important part of science, which also the University of Eastern Finland practices while making research about peat. The focus in the research is more or less focused on the amount of water and plant growth. When watching peatlands from an electric point of view, it is easy to recognize them as charged fluid interacting with its environment. If we take geological formations, their composition, hence the charge potential of them as a stable factor into account, we also should expect some visible electromagnetic separation taking place. Different parts of rock formations have different charges, and when they are connected, a current will flow between them. In calm conditions, like now, the current is rather weak, but I think sufficient enough to produce patterns. Like in the above mentioned article, where the focus of these patterns is on the moss growth, it is the easiest way to see them. Different mosses prefer different kinds of nutrients, and I think they are separated by electric currents and their magnetic fields within the wetland. The following pictures show exactly this. The water level plays a big role too, not only because of the volume, but also because it could change the connections between the bedrocks and therefore change the visible pattern. Here, on the right side, Mr. Too Tough making an electrical vortex that spins around this. And here we have some ferro magnetic things, and here we have a picture of a peatland in Finland where we have these structures. And I think they are aligned to some magnetic fields within the ground. So, let's jump a little bit further because let's jump back into here. We couldn't jump too much, but I don't mind. Maybe I have to brew some coffee soon because that's already a rather long video. Our modern society is very reliant on electricity. The invention of batteries was a further step into the age of mobility, and portable electricity was something that made many new things possible. Now we are going back to the nodules at the sea floor, the pebbles, about the producing of oxygen, about them being batteries, about I'm talking basically probably about the biggest batteries no one ever talks about, peatlands. And we are now at the base of the paper. So anyway, the modern alkaline battery was invented in 1950 by the Canadian engineer Louis Urey. An alkaline battery produces electricity by a chemical reaction between potassium, zinc, and manganese. Other versions with different materials were also available. We have the same ingredients in batteries as we have in many peatlands. So we also have to expect similar reactions happening in peatlands. The analogy between alkaline batteries and peatlands underlines probably in the best way that they are a crucial part of Earth's electrical circuitry. The drainage of peatlands has possibly a much greater influence on weather, flow of telluric currents, and the general circuitry of Earth than is anticipated. Lack of water reduces the conductivity significantly. Local weather patterns will be influenced greatly in a short amount of time when a peatland is dried out. The author thinks the main reason is that the energy created within the peat battery exhibits a certain magnetic spin direction when the land is dried out, the battery is broken. This could have such consequences as significant decreases in the formerly prevailing vortex direction, or even a switch in the direction. A clockwise spin, i.e., which would keep the moisture coming in through rain or creating the foggy environment, into a counterclockwise spin, which creates a high pressure system and therefore dries out the area even more. So, peatlands, in my opinion, are batteries in nature and they are very, very important. Let's just read this little piece of that paper and then I still have to show you some other stuff. Nonetheless, we have a charged environment and strongly fluctuating telluric currents, which easily can make stuff light up in different ways. The fact alone that there are several ways to have something glowing in the dark is a rather strong argument for an electrical explanation of the jack-o'-lantern phenomena. Let's go quickly to something considered very finished, the Kalevala. In the first part of this paper, the author quoted part of the Kalevala. A few sentences describe the theory of the formation of peat already then. That the aurora might have played an important role in the event is a conclusion made by the author rather recently. It is not known to the author in scientific terms or by experiments what actually would happen if the aurora would touch the ground. We can assume that the hot material, if the heat is maintained all the way down to the surface, would trigger some rather fast reactions in materials present on or in the ground, such as you and me. Things like water could experience rapid expansion, much like a phreatic volcanic eruption. That could produce massive shock waves. The emitted noise of such an event should be taken into consideration too. Acoustic shock waves also carry current. The abundance of water on Earth must be taken into the thinking of shock waves propagating through the environment. So now we are going to the part 3. No, part 2. We were in part 3. Sorry for that. Anyway, I didn't really plan this video. There's just a bunch of things I would like to show you. Yeah, actually here we have the iron well. I have been talking in the other paper. I made many videos about this. The iron well. But I wanted to show you something still about nodules, about oxygen, about the production of oxygen. But this time we are talking about a big nodule. Here it was. I made this overlay. Here we have the Markov convection. And this circle is this circle here. And if we zoom in, or when or as we zoom in, we find hydrogen and oxygen. On the outer periphery of Earth, because I tried to represent, this is basically a Birken current. At the center of the Birken current we have the heavy elements, and the lighter elements are obviously on the outer side. So Earth is, or I think has at the center, a plasmoid, which I think I described in this paper too. Maybe it's this paper. Let's go down quickly. Anyway, it was too difficult to find it in the paper, so let me show you just this picture. I think at the center of Earth, so to say, we have a plasmoid that provides the heat. The energy is provided by the Birken current, which is not visible here in the picture. And there's this kind of a precipitation thing going on from the inside out, where we can see, like, for example, that's some lab plasma in a ball, where it makes the connection here to the outer boundary. If this would be Earth's crust, this layer, this stuff would go in beneath, or go on beneath the surface. It's basically like a geoid, but alive. Same principle. Like a geoid, there has been a current flowing through the geoid that made the water boil, that made the stuff going in this direction. Maybe the same principle as the nodules were formed. Induced currents formed the nodules. That's why they are this kind of spherical balls that exhibit layering, because electromagnetism layers or separates different elements according to their electromagnetic properties. So that's from the paper again. You have probably seen my microwave videos where I created some very small parts of the Kalevala. That's the skirt made of fire, as described in the Kalevala. And we see an electrically charged rock here, a pebble. And most of the pebbles that reacted in any way in my microwave, they started in a way from, the reaction started from the inside out. That's the reason for why some of those pebbles are exhibiting the layering that goes outwards. Quickly back to this rock. This black stuff was quite likely created by induced currents into the pebble. This is in a way maybe burned sulfur, vitrified sulfur combined with other materials and stuff like this. And for example, this greenstone. Here we have the darker stuff in the center, but the reason is different. The reason, or let's say basically, the whole stone should have the color of that, or maybe even darker. But if you smash a window, or like if you find a pebble made out of quartz out in nature, it's usually white because it got smashed into something. So the crystalline structure gets deformed, it breaks, and it gets milky. So the outer side of this pebble, this part, indicates that this pebble has been smashed into other pebbles many times. And I think this has happened in very strong winds back in the days. So that's a different reason for a layering in a pebble. This is only mechanically, basically this layering, this part of the pebble, I think. That's the pristine rock, that's broken rock, so to say, because it got smashed many times into other rocks. And that's yet another prime example for rocks having a core. Here, I think, has been the greatest energy density, that's why the material melted at the center of the stone. Same principle as the center of Earth is hot, the biggest concentration of energy. Yeah, anyway, there would be still many, many other things to show, but I think I leave it here. I don't know, I should figure out some name for this video, nodules, about. You can find many, many, many videos on the internet how people create oxygen with very simple like some batteries and a few washers, and it doesn't need much in order to create oxygen. Basically, it's just a little voltage from somewhere, and now, as you heard something about the alkaline battery, you can find alkaline batteries that are as big as whole countries, basically. Peatlands. But anyway, let's see. There's so many other things I would like still to. Yeah, maybe another time. Thanks.